Buongiorno, signori. Ni hao. Guten Morgen. Well, let me try to contribute some aspects to the conference today. Maybe these are things you will not find in Google or in Wikipedia or in any kind of these online libraries. So, well, as this is the Department of Geosciences of Physics, I focus a little bit on this. And actually, we have some different methods in geosciences. So we have geology, geophysics, geochemistry, crystallography, petrography, mineralogy. And, well, I'm coming from the University of Basel, and actually it was in the year 1838, not 19, but 1838, that the expression of geochemistry was already created in German. It was geochemie. So this was Christian Friedrich Schönbein who created or designed this expression. Well, if we are looking on the analytical methods in geochemistry, there are a lot and very different methods. So what you see on the left-hand side in green, this is just UV with near-infrared spectrometry. Then FTIR, this is Fourier transfer in spectrometry. Raman, LIBS, Mösbauer, this is an older method. And then with blue color, we have the X-ray beam we are using. Then we also can use the electron beam. This is EPMA. This is TEM or SEM, the scanning electron microscopy. And many other methods are available, but they are more or less destructive. Like if you use the proton beam, then you have strong remanent radiation. You can use neutrons for NAA, this is neutron activation methods, or atomic absorption, or other methods like ICP mass, which is very common now today. Well, actually, it was Wilhelm Conrad Röntgen, the man who discovered the X-rays. And this was in 1895. So he did research on gas, and he found some rays he could not identify. And this was the reason that he called them X-rays. And still they are called X-rays. Now we know what kind of rays these are. But at that time, totally unknown, so he just called them X-rays. But in German, we still call this Röntgen rays because of the name of the discoverer. So he studied at the University of Zurich, where I am located with my company. And now it's over 100 years that the X-rays are used in different fields, very different fields. Everybody of you know this. If you go to the dentist today, he's also using X-ray to get a picture, to get an image of your tooth, which one is okay and which one is not okay. So many fields now in sciences using X-rays. So, well, state of the art in ED-XRF, what is it and what can it do now? It's energy dispersive X-ray fluorescence spectrometry. So we are using a spectrometer to analyze the samples. Well, something is very important to mention. If we are doing chemical micro and bulk analysis, we are saying XRF, X-ray fluorescence. But this expression was used already 50 years ago. And at the beginning, only WXRF, you find it on the left side, the wavelength dispersive X-ray fluorescence was in practical use with the instrumentation. It's very much different from this what we call ED-XRF now. And the reason is that we are using in WXRF a sequential analysis. This means we are analyzing one element after the other. So this takes a very long time at the end, but we get a very big result. With ED-XRF, we have a simultaneously analysis. So all elements are analyzed at the same time, just with one spectrum. So this is a big advantage. The disadvantage of WXRF is that we, besides the long measurement time, we also have some damage. We have radiation damage. That means if you would put a gemstone like a ruby, which is red, in the WXRF instrumentation, it will change the color to brown or something else. So with ED-XRF, no color change or no kind of damage will be caused. Well, if we have such beautiful stones like this pair of peridot 263 carat, you would never try to take any sample or to touch the stone. This is, of course, not possible. Or another stone, very, very nice. Here, the biggest Spinel from this important find in Tanzania, Mahenge, so over 100 carats. So this is very important to do a carefully analysis, but never take any sample or touch the stone. And anyway, get a full result of the stone and know what it is. Well, the customer demand also has changed dramatically in the 3 decades according to the instrumentation which are on the market. So WXRF, maybe it was in 1990 that 500 units have been sold worldwide. Now maybe only 100 units. With ED-XRF, it's just the other way around. So in 1990, maybe 100 units have been sold when the first instruments have been on the market, and now over 10,000 units are sold worldwide. Well, this was 30 years ago when we designed the one of the first ED-XRF instrumentation at the University of Basel. It was 1988. I remember that date when I started with the instrumentation. And actually, we were so happy. What did we analyze at that time? These were ancient coins from ancient sites. So archaeological finds in Switzerland or in Europe, and these are the first coins of pre-Roman times. So what we see when we analyze such a coin, it was already a complex silver alloy. So it was 90% silver, it was approximately 10% copper, and some very significant traces we did not know before. We find gold traces, so we could locate the silver deposits in Europe with the gold traces, and we find some traces of lead, which is coming from the production process, which is a cupellation process in the ancient times. So at that time, it was looking like this. Later on, this was just 10 years later when we set up the first measurement routine for rubies and for sapphires, and this was a big work we did on the Tracer Northern Spectrace 5000, and this was one of the first machines available on the market, and also the same analysis was done at GIA, so we had a sample set of 10 samples, and we analyzed in Carlsbad and in Basel at the university, and we could differentiate between natural and synthetic rubies. So this was published in Gems and Gemology in 1998. The older ones of you may remember this important publication. Well, then it was 2002 when I set up the first instrumentation at a live show at Basel World, and everybody was interested and said, oh, how fast is this instrumentation? And at that time, so small, it was a tabletop because the first instrumentations were very big size and liquid nitrogen cooling, and this was now an electronic Peltier cooling system. More convenient, and just we could run it at the booth and the customer could bring the stones. Well, it was 5 years ago when I went to Shanghai, outside to Kunsan, to this high-tech area, And when I visited Skyway Instruments and they invited me and I was going through the production and all this instrumentation, they have several hundreds of instrumentation, different instrumentation for very different applications, from food analysis to atomic absorption. And so I find two instruments which are suitable for GEM analysis, because something is very important. If you buy an ED-XR unit from a commercial producer, then it is normally not useful for gems and minerals. It's designed for metal of all kinds of precious metals, or copper alloys, or titanium, or whatever, for solid, and now at the moment more or less for petrol analysis, because this is a big market, or for food analysis, but never for gems. And your instrumentation has completely to redesign if you want to analyze gems and if you want to get good data. You can very easily get data, like with laser ablation, ICP mass, but all this data is usually not good if you do not calibrate the instrumentation properly. So, well, what I did, I introduced the engineer how to redesign, how to change the instrumentation that it is useful for the geometric applications and for minerals or glasses. Well, there has to be an optimized hardware, of course, so the X-ray tube with the rhodium anope, a fast STD detector, fast digital pulse processor. The distance must be optimized between the sample and the X-ray beam. Then the filter material selection, then thickness of the filter material is very important. The power supply unit must be controlled properly. Current controller, dead time counter, all these are things which are very, very important to achieve at least a high stability and a repeatability for the results. So also the software must be optimized, and many, many things have to be changed that at least you get good data. Well, this was the result after, let's say, 2 years in investment. We designed the instrumentation that I called GEMRAY. It makes sense. It's only for gems, so we use the X-rays for the gems, and this was my idea. Well, how can we satisfy the customer? Well, we have to design the ED-XRF instrumentation that we achieve high precision, high resolution, high stability, good repeatability. So this means also the data has to be always the same. If you have the same sample and measure it 5 times, 10 times, you always have to get the same result. Otherwise, it's not good. Then, of course, low detection limits, because you want to analyze the traces. These are important to identify locations, deposits, and so on in gemstones. Then the error should be also very low, and the standard deviation, and then maybe you get excellent data, and you also want to handle the instrumentation easily. Well, why do we need this in gemology? The answer is relatively simple. Your testing report will be never good if the data is bad. So what we have to do is to set up first the whole procedure with standards. What you are seeing now is titanium. It's just a titanium diamond, so you see what you can do with titanium. Titanium is not only metal as basic, but you also can have an oxide and that can produce a titanium diamond. This is pure titanium. Titanium is a very common element, very important in chemistry. You have it everywhere. Even the plain white paper is titanium coated. The white walls are titanium pigments, but this is a titanium diamond, and with this titanium diamond, we calibrate the titanium lines in the spectrometer. So this is a K-alpha titanium line and the K-beta titanium line. We are calibrating with this sample. This we have to do with each element from atomic number 11, this is sodium, to atomic number 92, this is uranium. Each element has to be fixed and to be calibrated with pure standards and reference material, otherwise it will never work. Well, let me show you some spectra, some examples of this. the spectrum is always the source of analytical information. So we just will have a look shortly on some garnet, some apatite, sapphire, spinel, beryl. I see the E is changing here. Sometimes I prepare this on Mac, but Windows does not accept them, so they just change a little bit the pictures. Yeah, calibration, yeah. But this actually has nothing to do with calibration. It's just the Apple Windows war, yeah, since 30 years. Well, this is a demantoid sample from Namibia, a mineral with many, many small crystals on top. And so let's take one and have a look on the spectrum. So what you see on the horizontal axis, this is the energy line. The vertical are the counts. So you see there is Si, there is Ca, and Fe. So this is what we find in demantoid. So we have no trace elements. Usually demantoid is very, very pure. Well, totally different is some blue apatite from Brazil, and with many, many traces, thorium, uranium, arsenium. Green apatite is also very different, full of trace elements you will never see with any other method in this way: arsenic, strontium, yttrium, thorium. Then we have some spectrum from sapphire from Pakistan. So typically is titanium, vanadium, chromium. High traces of Ga, zirconium. Then a ruby from Madagascar with titanium, vanadium. Big green peak, this is a chromium of 1927 ppm. So let's shorten this one. You get a chemical composition of ruby from different deposits. Then you can differentiate the deposits to locations. Well, something we cannot have a look now because the time already, they say I only have 3 minutes. This is the very important gold chin sapphire with very interesting traces. Let me show you some blue spinel from Sri Lanka because this is interesting. You have Fe, you have Zn in this sample, and if you are looking on the important traces, you have besides the zirconium also uranium, and this is producing the typical bluish color in this stone. Well, this is a chemical composition of spinel. You can set up such a data table within 3 days if you are concentrating, working. The instrumentation are very fast now. And let me finish this with some fuse from emerald from Zambia, which is very, very typical with a cesium. So the 2 peaks in the right side, the high ones, this is cesium, and typical for Zambia also rubidium. This is a flux emerald, a synthetic, totally different. You have no cesium, you have low rubidium, you have some arsenic traces. And last not least, it's also possible to analyze cultured pearls or freshwater pearl or whatever. So this is significant here. If you look at the pearl, you will say, oh, wonderful, silverish, beautiful, but actually it's an AGIL treatment, and with this method of ED-XRF, we can analyze and we can identify in less than 30 seconds that this is not a real true pearl, but it's just an AGIL treatment. So, well, thank you for listening. The customer is precious for us and not only the stones.